my Lab 5 modeling effects of air resistance on free fall video development. In this lab, I'll be looking at Felix Baumgartner's monumental jump from 39,000 meters, which is the highest jump made by a human recorded in human history. I'll be analyzing the physics behind his monumental jump, specifically how air resistance as well as changes in air density and temperature affect his free fall speed. The main results of my lab, I compared the straightest data of Felix's jump to a GlowScript generated model of ideal free falling motion. And here are the two data sets. The graphs of the two data sets can be observed here below. The purpose of this lab is to analyze how Baumgartner's vertical jump from the stratosphere compares to an ideal model of free fall when an object of the same size and mass as Baumgartner. And the other main thing I'll be looking at is how air resistance affects Baumgartner's velocity with altitude throughout his jump. System and surroundings in this lab. The system is the free-falling object, or Baumgartner in the straightest case. And in this particular case, the surroundings are exerting forces on the system, with the Earth supplying the gravitational force that's being exerted on the system, and air supplying the air resistance force exerted on the system. The fundamental theory and principles used in this lab are Newton's second law relating force to mass and acceleration, the velocity and position update formulas, as well as the air resistance formula, which states that the force of drag is equal to a half times the density of the fluid, which in this case is the density of the air, times the velocity of the object squared times the drag coefficient, and multiplied by the object's cross-sectional area. The experimental procedure, I'll be looking at the vertical velocity versus altitude data of Baumgartner's jump from a POV video of his jump, and I'll be deriving the data from that particular video. I'll then generate a GlowScript model based on his bodily dimensions, comparing altitude to velocity, just like I'll do in Baumgartner's video, and then I'll compare both models to each other. Initial conditions of the slab. In order to compare Baumgartner's jump effectively through the GlowScript generated model, we need to create an object that matches Baumgartner's bodily dimensions, both in the weight, height, and width. Here, Baumgartner's mass, height, chest width, as well as the height he jumped from. The experimental assumptions are that in order to create an object in the GlowScript model that matches Baumgartner's dimensions, I assumed from average male statistics that Baumgartner's chest width is about 50 centimeters. So in the GlowScript model, I'll create a rectangular object to represent Baumgartner. That's his height, has his height of 173 centimeters, and his approximate chest width of 50 centimeters. Another assumption is also that the only forces acting on the free-falling objects are the force of gravity and air resistance, and that in the GlowScript model, the air density will be assumed to be constant at every attitude. The straight and jump data derived from the POV video can be observed here, where I compare the velocity versus the altitude of Baumgartner throughout his jump. The GlowScript code used to create the model. Here are the initial conditions of the model, where the mass of the object matches Baumgartner's mass of 73 kilograms. The initial position is approximately 39,000 meters above the ground. The gravitational acceleration is 9.8 meters per second squared. The estimated average density was, as mentioned earlier, 0.215 kilograms per meters cubed. The surface area derived from Baumgartner's height and approximated chest width was calculated to be 0.85 meters squared, and the drag coefficient was approximated to be about 1. The calculation loop, I basically, to find the net force that affected the object's motion, I added together the force of gravity and the force of drag. The force of drag obviously was calculated using the air resistance formula used earlier, and I added both forces together to find the net force. This net force was used to update the velocity of the object, and from that, the position of the object as it was falling. Here are the GlowScript model results. I put them in a Excel graph just to ensure an easier comparison with the Stratus data. As can be observed here, the models look very similar but don't match each other perfectly. The GlowScript generated model has a higher peak just because I did not account for the higher error density at lower altitudes in the GlowScript model, and I used a average uh, weighted air density for the model, which is not an accurate representation of how air density changes throughout the free fall. Possible source of error, the fact that the air density at altitude changes as well, which was not accounted for in the GlowScript model, and the fact that Baumgartner's body was modeled as a rectangular block, which in the GlowScript model, which wasn't an accurate representation of his actual stature. The discussion part of this lab, how the changes in air density with altitude have effects on my predictions. The change in air density would certainly affect my model predictions. As mentioned earlier, the air density does increase as the altitude changes. As the object falls lower and lower down towards the ground, the air density increases, and as air density is part of the air resistance formula, this means that the air resistance would increase exponentially as the object approaches the ground, resulting in higher and higher air resistance, which is what actually caused uh, the Baumgartner to slow down during its free fall, as shown in the Stratus data earlier, and also what affects the temperature change with altitude has on my predictions. Um, Basically, this boils down to the fact that higher temperature at lower altitudes results in the air particles moving around quicker, resulting in more collisions and a higher air density, which, as mentioned earlier, results in higher air resistance. So, if I was to account for the temperature change as well with altitude, then the air resistance would be even greater at lower altitudes.